Hello. This will be a demonstration of Proposition 8 from Book 10 of Euclid's Elements, which says that if a magnitude has not to another magnitude a ratio which a number has to a number, then these two magnitudes will be incommensurable with one another. We're given two magnitudes, A and B, such that the ratio which A has to B is not the same as any ratio of two numbers. It is not the same as any ratio which a number has to another number. And what we want to prove from this is that A and B, our two given magnitudes, are incommensurable. For if this is not the case, then they will be commensurable. But if they are commensurable, then we know from Proposition 10(5) that they will have to each other the ratio which a number has to a number, so that A will be to B, just as a number is to another number. But this is contrary to our given, which says that A has not to be the ratio which a number has to a number. So if A is commensurable with B, then A will both have to be and it will not have to be a ratio which a number has to another number. This is obviously absurd, and so we can conclude that A is incommensurable with B. This being what we set out to prove, we are therefore done with the proposition, therefore, etc. QED. Now, they're contrapositive, much like the last one, and the logic is virtually identical. In fact, I didn't erase any of the reasons except for exchanging 10(6) out for 10(5). Besides that, all the reasons are identical. This is the second last proposition in a set of propositions relating magnitudes to numbers, which is a huge move both for geometry and for arithmetic, which Euclid had put side by side in the Elements and up until now seem to be two distinct fields of mathematics, but in Book 10 we're seeing how they converge. Before I close out the video, I always like to give an example, so let's do that right now. Just like last time, we'll go with the classic example of the diagonal of a square. So say we have some square whose side is a b, like so, and we join its diagonal AC. And if we can show that the ratio which AC has to AB is not the same as the ratio which a number has to another number, then what follows is that AC and AB are incommensurable. This is, again, just like I mentioned last time, this would lead you into the classic proof of the irrationality of the square root of 2. For if we say that AB, if we number it 1, then we can number its diagonal AC as the square root of 2. What, of course, that means that the square on AC is 2, where the square on AB is 1. And if we can show that if the square root of 2 has to 1 is not the same as any ratio which a number has to a number, then what follows is that they are incommensurable. How we would put this in modern notation, we would probably not say this in the language of ratios, not because it's wrong, but it's not conventional. Rather, what we would say is that if we can show that root 2 is not a ratio of two integers, if we cannot represent it as a fraction of two numbers, say A and B, right, where A and B are integers, or just numbers, then what follows from this is that the square root of 2 is irrational, that it cannot be represented as a ratio. Again, you can find this proof set out in detail in all sorts of videos. Again, this is one of the most famous math proofs of all time, so you can find this virtually anywhere. That's all I've got to say about this proposition, so I'll end the video here and move on to Proposition 10(9).